So u equals to s of t, e s of t. Given s means given complex exponential. Okay? Now, if I take cosine of omega t, what is it going to be? It's going to be e j omega t minus e minus j omega t divided by 2, if I remember correctly, either a plus or minus here, either a 2i or a minus 2i down here. But in a certain sense, a cosine is the sum of two exponentials where the s is with 0 sigma. Are we together on this? Perfect. So if I take this one, it indicates that I've got a sigma that is with the real part negative. True? If I was seeing something that was staying, it would be something that was like this one. True? If I take the opposite one and I sum them up, I get either a sine or a cosine. Are we together? Perfect. This is general. So the discussion that we do now works for all the cosines and sines. Okay? Because the sum of star plus square is going to be integral of sum plus integral of square. True? So all the stuff that we do now is in general. And now this is going to be this. I expand this stuff and I take out this one. What can we say? Complex exponentials are eigenfunctions for LTI systems in the sense that I inject EST, I have the convolution, and I get the same EST times something. Together? How much are we together, people? 1, 2, 3. Perfect. If this one is a cosine, this is going to be a cosine, and this is going to be something. True? And if this one is going to be 10, 7.3 t, and then we get the same cosine times 10. And then here we change, we put 100, and here we get 0.9. Do you see that in a certain sense, this number here is actually the stuff that we are looking for. True? How much are we together on this, people? 1, 2, 3. We need to understand what that number is. And we kind of understood that whenever we have the transient to 0, from a practical perspective, we can consider this one. True? In a certain sense, it's going to be the steady state. True? This one is wrong. It's j omega t. There's a typo here. Send me the email of the typo. Somebody sends me the email of this typo here so that I fix it. And if we look at bibostable systems, and this is the formula, so it's with a plus. What am I plotting here? Here I'm plotting the exponential and the cosine that is I think it's the cosine associated to the exponential. If I take this object here, let's focus on this object here. If I take a bibostable system, this one in time, what does it do? It goes to 0. True? And if I take this object here and I multiply times this object here, it's this image is wrong because the red one that represents this one should kind of stay in the same with the same spiral. True? If I multiply those two objects, the impulse response that goes to 0 and a spiral that stays, what happens? It happens that this stuff, for plus infinity here, this object is going to be a finite number. Do you see why? If I take h that is Bibel stable, it means that the h is going to go to 0. True? Are we together? And if I take the integral of a function times another function that doesn't explode, this is going to be something that, in a certain sense, is going to be what? It's going to be a spiral, complex spiral, that goes down to 0. And if I do the integral over t, it's going to be the integral of the real part plus j, the integral of the imaginary part. The two components are going to be finite. Are we together on this? I see puzzle faces. Let's make it in real. If I have h and I have this is my sine and this is my h. If I multiply them, do I get something that goes to 0? Of course, we will get something strange that will go to 0 because this one goes to 0. True? And then if I take the integral over infinity of this stuff here, can it explode? No, because it goes down exponentially. True? Because we started with a Bibel stable system. True? Do we see that if we do this for the real part and the imaginary part is the same concept? So if we have, imagine this red line to be kind of a spiral that stays, okay? But do you see that it's the same concept? Here in gray is the impulse response. Those two numbers are finite for t that goes to plus infinity, okay? What does it mean? It means that if I go back here, if I take this u, that is a spiral, the force is going to be u itself, that is the same spiral, times a number that is going to converge to a complex number. True? And if I take a complex number and I multiply it times another complex number, what am I going to do? I'm going to amplify it and rotate it. True? Do we remember this about complex numbers? Real part, imaginary part. And then I have my number star, and then I multiply it times number square. The product will be what? The phase is going to be the sum of the phases. The modulus is going to be the product of the moduli. True? Are we together on this, people? 1, 2, 3. Do we remember this? If we don't remember this, this is very problematic. Okay? If we don't remember this, this is very problematic. Okay? Together? Perfect. Now, if my star is E j omega t, this point here, how does it look like? It looks like something that does like this. True? True? Perfect. Now, if I take this star of t and I multiply times a fixed number that is of magnitude 3 and of phase 60 degrees, okay? My original star was doing this, true? And my star multiplied times square, let's make it in violet, is going to be what? Where does it start? Does it start, before it was starting here. Now, where does it start? It starts at 60 times 3, true? And it does like this, true? That is the same rotation with the same speed, but it starts amplified by 3 and shifted of 60. Are we seeing it? 1, 2, 3. So, I have U, and I take that is a spiral, and then I've got the force t, that we saw that from a mathematical perspective is going to be u times a complex number, finite complex number. This is a spiral. This is going to be, for t going to infinity, a finite number that will be something that from a complex plane is going to be a certain modulus and a certain phase. True? What is going to be this? This is my A, and this is my phi of the shifting. Do you see it, people? And of course, if I change this, sorry, that's a typo. If I change this number here is going to change. True? So maybe for omega well equals to 10, it's this number here. And maybe for omega equals to 7, it's going to be this number here. You see? So whenever I inject a cosine with this frequency, it's going to get amplified and shifted of another value. How much are we together, people? 1, 2, 3. What did we use? We use the fact that this stuff here is Bibo. Because if the stuff here is Bibo, then this stuff here converges. And the fact that it's linear time invariant, because if it is not linear time invariant as a system, this operation here that is falling from the convolution, true? It's falling from the convolution. That operation wouldn't be defined. If it is not a linear time invariant system, I can't write this stuff here. That means I can't write this stuff here. That means I don't have these. Okay? With all the caveats, because in a certain sense, whenever a system is nonlinear, for example, if I've got an ODE that looks like this one, y dot, if I stay here, it's like it's linear. Together, perfect. That I can use impulse response and convolution. And impulse response and convolution implies that eventually u, that is e j omega t, is an eigenfunction of an LTI system. That means the y is going to be the same e j omega t times a factor. This factor here for t that goes to plus infinity, that means whenever I converge in terms of steady state, this number here is going to be finite, complex. That means amplification and shifting. Read this stuff. Read it and tell me if we are together. Very much? Not at all? Kind of. H. H. This is H. I've got to go through a couple of things. And is stable in the sense of Bibo stable. Whenever you feel like you got it, you can answer. Show me the fingers. Okay. As it's not easy stuff, okay, people? We are doing it not from a mathematical perspective in all the correct ways, but I want you to get the intuitions more than the formulas, okay? And it's not easy stuff. At home, think again about this. This is a very central concept in automatic control, okay? Yeah, it's the same stuff. Okay? That means that, key fact, stable in the Bibo sense, LTI systems preserve sinusoidal shape after a transient. And only the amplitude and phase change, and those ones are going to be functions that I can plot. How many of you heard about Bode plots? I am Bode, don't even know what it is. Those are Bode plots, true? Bode plots, for the people that do not know, are opportune representations of this stuff here. So imagine this one, written in this way. Omega amplification factor, this is H. Okay, because the W is the closed loop, but it's the same. This is H, modulus of H, J omega. If I draw something like this, it means that somehow around 10, I've got some resonance. True? Together? And then I might have some phase shift, but this typically is kind of less important. Okay. Let's make a drawing. Tell me.
These final results that we obtain with the vanishing term. The vanishing term should be the free evolution, right?
Yeah.
And how can, is this general or is it related to the fact that we must have a certain type of transfer function?
It's actually a bit. So we need to have Bibo stability. Let's make a question out of this question. Sigma omega. I'm representing everything in Laplace. U is red. H is gray. Okay. If I have an H that is looking like this one, can I apply the concept of sinusoidal fidelity? Yes, no, I do not know. The question is that H Bibo stable? If I've got this H, can I apply sinusoidal fidelity? No, perfect. If I have this U, can I apply sinusoidal fidelity? Yeah, we go to zero, so eventually everything is zero. In a certain sense, it's a sinusoid of zero. 0 times sinusoid of 0. If I apply this one as a U, can I talk about sinusoidal fidelity? Perfect, yes, it's like the situation, true? We are going to see very soon, mathematically, can I apply sinusoidal fidelity in this situation here? What is this input? This one is the step, true? And if I look at y total, and I get a y total, for this input, I get a y total, let's say, this is a step response, true? This is a step response. And I've got the amplitude of the input and the amplitude of the output after the transient goes to zero. Do you see it? Isn't it the gain of the system? And step of t, isn't it cosine of 0t for t bigger than 0? So it's the same. Sinusoidal fidelity, a step is a very special cosine, and whenever we think at the gain of the system in terms, I put 2 volts and I get 7 centimeters out, my gain is 7.5 measurement units. That is a special case of sinusoidal fidelity with a cosine that is a degenerate cosine. Okay? So we are talking about the same exact thing whenever we are talking about steps. Can I talk about sinusoidal? Are we together that we still are talking about sinusoidal fidelity? 1, 2, 3. Oops. Perfect. If I have this input here, how does this input look like? This is a ramp. True? It's the integral of a step. True? Can we talk about sinusoidal fidelity in this case? No. Can we talk about sinusoidal fidelity in this case? Discuss. What would you say, people? Question. Yeah. Yeah. I can consider, I cannot, I do not know. Be honest. U is going to be this plus this plus this. True? And if I do convolution of this stuff, convolution times h, isn't it h convoluted by times this plus h convoluted times this plus h convoluted times this? True? Isn't it linear? Would we have superposition of the steps? Perfect. I can apply here, I can apply here, I can apply here. True? It's trivial as an answer as soon as you think that it's a sum of components and we have superposition of the effects because it's LTI. How much are we together on this? 1, 2, 3. Okay? Okay? Perfect. Names, amplification, attenuation of input sinusoids at omega, phase shift, static gain, and nothing. If the system is not stable, let's read this together. If the system is not Bibo stable, the divergent terms dominate, there's no meaningful steady state. If I have a situation like this one, this stuff goes to infinity, or better, diverges. True? We don't have a steady state. Stuff explodes. True? Together on this? Perfect. If this is interesting, this one is extremely interesting, people. Marginally stable, that means poles on J omega. That means that my H looks like this one. Okay, this is my H. Then, if the input sinusoids are at the same frequency, and this is my U, the Y is going to look like something that decays, decaying terms, plus T sign. True? Potentially amplified, potentially shifted. True? Hmm? It's a divergent output. Those ones, actually, you might still compute them with the formulas before, even if it's not very, very meaningful to apply them. Okay? But you see that in a certain sense, you still have an amplification and a shifting. Are we together? And that amplification, that shifting might depend on that omega. Are we together? Perfect. If instead I've got H, so H that looks like this one, but U looks something different, Y, will Y diverge? Yes, no, I do not know. Discuss. Do you see the colors that are different? Let's say that the green one, we make it a little bit thicker so that you see. And this is my U. Discuss. Will Y total diverge? Together? Are we together? No, it doesn't diverge. Okay? When does it diverge? Because if you think at a Laplace, it's the Y is going to be the sum of all the components. Some components go to zero, some components stay sine of a certain frequency, some components stay sine of another frequency. Okay. And then whenever you do the sum, there's Euler formulas, true? Indeed. Sorry, this is the limit case. You got the point. This one should be the one before. Hmm? We have this phenomenon for which, watch out, this is the product and the orange is the area that is equal to the value of the y. This is the y, okay? Okay, are we together? The y, you've got those resonance. The closer the two frequencies are, the more the peak, okay? But still, you're gonna have that y is gonna be a certain cosine omega t plus, let's say this is omega, and this is omega prime, cosine omega prime t, and you will have an amplification factor and a shift, and another amplification factor and another shift. How to compute them? Other formulas, but the concept is the same. How much are we together on this? Perfect. Then let's do a last thingy. I don't remember. See, I'm dumb because I put some stuff and then I forget to put some other stuff. Where did I put the videos with the moduli? I'm dumb. I am dumb. Manim, those ones. What are we seeing here? Modulus of a generic transfer function. This is modulus of h of t, h of s, real part sigma, imaginary part omega. Where are the crosses here? How many crosses, how many poles do you see? Three. Three poles. True? 1, 2, 3 poles. Are we together? 3 poles? Perfect. How many zeros? Do you see them? There's one here, one here. I do not know if you see. If I will replot it with logarithm in a logarithmic scale, it will be kind of something that goes down to 0. H of t, Bibo. Okay? Can I apply sinusoidal fidelity concepts? Yes, no, do not know. Yes. That means that I need to plot the function modulus of h j omega as a function of omega. True? I've got to plot this function here. This function here is my stuff. True? That's also the phase, but this is the amplification factor. Are we together, people? Are we together? Perfect. Now, let's take this object here. Sigma omega modulus of h of s. True? Because I've got h of s, and I can do modulus of h of s. I have, for example, 1 over s minus 3 plus 3, s plus 2. How does it look like, this stuff here? I've got a pole here and a pole here. True? It's kind of this and this, and it looks like this one in an opportune way. Are we together, people? 1, 2, 3. Where do we find this object here? Where do we find it? Sorry. We have a blanket. Let's make the blanket like this one. This is the 3D blanket of the impulse of the transfer function. We're together. This one is this blanket here. True? Are you visualizing what I'm drawing? And I want to find this object here. If I take this plane, the one that corresponds to j omega, what am I going to do? I'm going to cut this object here. True? I'm going to take this one, make a cut along the plane, and I'm going to find something that looks like, oops, my amplification. Okay. Do you see from a graphical perspective what I'm doing? Perfect. And then if you see it, I have sigma omega modulus of h of s, and I've got a system that has got pole, pole, and this is my h. Which system might have this specific h? Which physical system might be modeled in this way? Spring mass system. Spring mass system. Now, I've got a spring mass system with a certain K and a certain B. Y2 dot is equal to minus Ky minus By dot plus U. True? Okay, find the transfer function. Go. Find the transfer function here. Together? Together, people? 1, 2, 3. Perfect. What shall I do to the spring mass system so to have it not Beebo stable? How do I have to modify my spring mass system so to do not have it Beebo stable, so that it's not Beebo stable? Discuss? If this one is 0, it means that I have no friction. That means that this one goes to 0, true? And this stuff here corresponds to what? To roots that are here, true? Together? Perfect. Let's assume that I have a Beebo stable system. If I make B smaller, what am I gonna do? I'm gonna do that the poles kind of get closer to the imaginary axis, true? We are together. Now, let's assume that my U, from a Laplace perspective, it's this U here. Okay, together. And then I've got system 1 and system 2. Okay, together. Given the same U, the output, the max modulus of Y forced response of T, will it be bigger for system 1 or for system 2, or you do not know? System 1 is with more friction, and system 2 is with less friction. No? Discuss. Is the question clear? I've got the same U, and I've got two systems. One with a lot of friction, and one with not so much friction. And then I've got to look at the Y output. I will have Y1 and Y2, true? Which one will oscillate more? So people, what would you say? It's going to be bigger with 2, true. Less friction. Why? First of all, the frequency, this is going to be after the initial transient, is going to be a sinusoid, true? The two sinusoids, do they have the same frequency? Yes, because it's going to be driven by this frequency here, okay? So, will they have the same phase shift? No. Will they have the same amplitude? No. Think at this image here. If I move the poles around, the shape of the cone, does it change? No. I do not know how clear it is. Let me do it just a moment. If I have 1 over s minus 1, and I take the modulus of this stuff here, it's going to be the modulus of 1 over modulus of s minus 1, true? And this is the distance between the s that I'm considering and the x that I have, true? So, if I have this is my pole, let's make it complex, it doesn't matter at all. It's actually minus in this case, sigma omega. If I take s here, this one is the distance. I've got a height that is 1 over this distance. And if I go closer, my height will be 1 over this distance. True? Do you see it? Are we together? Do you see it? And if I take this stuff here and I move it around, it's the distance from the pole that is important. Are we together, people? 1, 2, 3. That means that here, whenever I move the crosses, the cone follows. True? And then I sum the cones. Actually, it's a product, but in a certain sense, you get the point. What does it mean? It means that whenever I do a lot of friction stuff, I have a cone. Oops. I have a cone and I have a cone. True? That means if I think at the blanket and the intersection of the blanket, what will I have? I will have something that looks like a bump. True? Do you see it? Do you see it, people? And if I take gray, I will have the cones that are closer by. So it means that I've got a higher bump. True? Are we together? Do you see that by putting the poles closer to the imaginary axis, I'm getting less and less bibostable? True? Because in a certain, and I'm kind of getting a cut for which I'm cutting closer and closer to the poles. True? You see? And then what did we say? We say that y total is going to be amplification factor times the cosine omega t plus phi. This omega is this one. True? And in case 1, the amplification factor is this one. And in case 2, the amplification factor is bigger because the cut is bigger. You see? How much are we today, people? 1, 2, 3. What is not clear? I see several tools. Other questions? Are we together that depending on the position of the poles, I have the cones, but the cones from a structural perspective, they are the same? How much are we together, people? 1, 2, 3. If I have this pole and I put it closer to the axis, I cut along the axis to find this function here. How is it? The fact that I cut along the axis to find a omega, is it clear? The amplification factor is this one, h, but we got the point. True? So this one is my amplification factor that depends on omega. I'm taking cones, putting them closer to where I'm going to cut. If I put them closer to where I'm going to cut, you should see it. It's kind of slicing the stuff closer and closer to the peak. True? So these, as I move the poles closer to the imaginary axis, this one lifts up. That means that my sinusoidal response is going to have bigger gains. Okay? The same concept applies on the phase. So also in the phase, you use a cut and move stuff around. But to be honest, this is more important. The modulus is more important. True? And then what happens whenever we lose stability? This is interesting. Whenever we lose Bibo stability, it means that somehow we are cutting where the poles are. True? So we have kind of a volcano that goes to infinity in 1 omega. And if I choose that omega for the input where I've got infinite amplification, indeed, we go to infinity. You see? A lot of stuff, but it's an important question.
So if we enter for example, the case one, where we are like, if the pole, so if the poles, considering that they have also a sigma component, are at the same height of the omega that is the u. In that case, also we have like, okay.
This is an interesting consideration. Imagine that we have a situation for which we have the poles. Let's draw only one. You got the point. It's symmetric with respect to the zero. Okay. We have a pole, and this one is going to produce a bump. True. If we have a situation like this one, how does the h of t look like? It looks like something like this. True. In a certain sense, for which u equals to cosine omega t will I get the biggest amplification? For which omega will I get the amplification? For an omega that looks like this. True? Do you see it? Do you see it? From a numerical perspective, no, actually it's it might be shifted. It's not going to be exactly the same omega. Okay, it's not going to be exactly the same omega. It's slightly more complicated from a formula's perspective, but at least you get the intuition that somehow if I've got a swing that is swinging naturally with a certain frequency, true, we have something that looks like this one, true. If you want to make the kid swing as much as possible with least energy as possible, true, you select the way of pushing the swing that in a certain sense complies with the natural frequency of the swing. How much will you do that? 1, 2, 3. Let's do this one, then we close it. Come on. As an answer or a question? Tell me. This concept that when you inject a sinusoid from a big flat system, you're going to get eventually sinusoid as a UP, the same frequency. So you make a sinusoid that is basically what we have been studying. Rewatch this. Okay, people, how are we here? How are we? After the transient. It's not very well written. After the transient. Together. Okay, people. I think we are there. This concept is very important. Okay, we went relatively slow so that we are all together. I'm not. This is one of the concepts that are the most important. One of the most important concepts from an automatic control point of view. Okay, It's going to be used a lot of times. Whenever you hear about Bode plots, they are logarithmic scaling of the plots that we saw up to now. But it's the same concept, okay? So be careful to get the messages here, okay?